Thank you for visiting my channel. I am the Actuarial Guy, and this is the second part of Unit 3, which deals with interest rates. Nominal rate of discount. The nominal rate of discount payable P times per period is denoted by this. We refer to it as the rate of discount convertible pthly or compounded pthly. Now you know that the nominal rate of discount is a rate that pays interest at the beginning of the period. If we have a nominal rate of discount that pays interest P times per period, we simply mean that in these P periods, this rate will pay interest at the beginning of each period, such that the total interest is paid P times throughout the whole period. Now, a nominal rate of discount per unit period payable pthly translates to a rate of discount of this, where your nominal rate of discount is divided by the number of times it pays interest, applied for each pth of the period. What I mean is that for each of the P periods, if you take 1 unit time, I always like using 1 year as our unit time. If you take 1 year as your unit time and you have a discount rate that pays out monthly, then your pth period is going to be 1 month. Your 1 over p is going to be 1 over 12. So for every month, your every 1 over 12 period, you have interest paid at the beginning of the month, and the interest paid is your nominal rate divided by p. In our case, our p is 12. Now, same as the example that we saw of the nominal rate of interest, we can also convert the nominal rate of discount to an effective discount. And to convert it, you need to apply this formula, where if you rearrange this formula, you can get your D. Your D here is your effective discount. So you need to remember that when you're considering examples, you need to find out whether the rate you've been given is an effective discount or if it's a nominal rate of discount before you go on ahead to answer the question. Alright, now we're going to look at the force of interest. Now we assume that for each value of I is the rate of interest, there is a number delta such that when your P tends to infinity, you have delta. The limit of your nominal rate of interest per unit time convertible pthly, where P tends to infinity, is equal to delta. Now we assume that this exists for each and every I. I'll give you an example here. So what we are doing here is that we are assuming that, say we take a rate of interest of say 12% per annum convertible monthly, where our P is equal to 12 because it is a rate that is convertible monthly, and our unit time is 1 year. So if we assume that instead of having P as the 12 months convertible monthly, we decide to have weeks. Now our P becomes 52 because there are 52 weeks in a year. Instead of having weeks, we make it even smaller. We decide to have days. Our P becomes days, so that we have 365 here. But then 365 cannot even be compared to infinity. So keep on making that period smaller such that you have your interest compounded, let's say, every single hour of every day. But that is still nowhere near infinity. Now if we keep breaking down that time interval and making it smaller and smaller and smaller till you get to 1 minute of each and every day, and then you can still make it smaller than 1 minute, you can make it 1 second, and then much smaller. Now if you consider that the period of compounding is so small that our p is close to infinity, we gain a value delta for our IP, where this p is close to infinity. This limit tends towards delta. Now what we're doing is that we are assuming that for every value of interest, be it 13%, 14%, 50%, this delta exists. It is not necessarily the same value, but it exists for each and every value of interest. Now delta is referred to as the force of interest, or the rate continuously compounded. We could say it is the nominal rate of interest per unit time convertible continuously, because our pth periods are so small, they get so small that it's almost as if we are receiving interest continuously. Now just a reminder here, you may have seen Euler's rule before. Now what Euler's rule says is that 1 plus x over n raised to the power n, where n tends to infinity, gives you e power x. Now we're not going to go into deriving this, but we're going to use it to derive something else. So this is it's Euler's rule. It's a rule that has been proved. If you're interested, just pop Euler's rule into Google and you should get an idea of how to derive this. So if we take the right hand side of this formula here, this is the formula we had earlier used to work out the effective rate of interest in cases where we were given the nominal rate. So if we take the right hand side of this formula here and look at how it may resemble this, there's a slight resemblance there. So let us introduce a limit where p tends to infinity. In our case, as p tends to infinity, we would have this, e raised to the power I infinity. It's infinity here because if you look at this, we had x here, and so it tends to e raised to power x as n tends to infinity. In our case here, it would tend to e raised to the power I p, ip, as p tends to infinity. But since we know that p tends to infinity, it becomes e raised to the power e raised to the power I in brackets infinity. Now remember that in our earlier slide we had defined this value delta as the limit of I p, where p tends to infinity. So in what we have here is I to with the compounding period of infinity here. So that actually translates to e to the power delta. Now the left hand side was actually 1 plus I, so we get that 1 plus I is equal to this. Now remember that our nu was given by 1 over 1 plus I, which is equal to 1 plus I to the power of minus 1. So since 1 plus I is equal to e to the power delta, you can see that nu is equal to e to the power negative delta. And if nu is it's raised to, let's say, a power of t, we have this relation, and as a result, this. So as a result of this, the discount factor for a force of interest delta is given by this, where this simply means, this nu n means that we are discounting over a period n, which would actually be given by 1 over 1 plus I raised to the power n, such that if you multiply this by an amount c, you would in effect get the value of c at a time n years before. That is why we call it a discounting factor. So in our example, this value here, 1 over 1 plus I, is equal to nu, but our nu is equal to e to the minus delta. So this raised to the power n is equal to e to the minus delta n, which is the discounting factor for a force of interest delta. Now we can also derive the force of interest by using nominal discount convertible Peatley, and we are able to show that the limit of this nominal discount rate convertible per unit time convertible Peatley is actually equal to delta. Now if you're interested in seeing how this can be done, just send me a message and I will do a quick video just for you. Once again, thank you for watching. I am the Actuarial Guy. Do not forget to subscribe in order to receive the latest videos from my channel.